The Fourier transform is a powerful mathematical tool used to analyze signals and functions. It decomposes a function, such as a signal or image, into its constituent frequencies. Essentially, the Fourier transform converts a signal from its original domain, often time or space, into the frequency domain. This transformation reveals the different frequencies present in the signal and their respective magnitudes. Here we can see how a complex function can be broken down into a series of simple sine and cosine waves. Each wave represents a different frequency component. A helpful way to understand this is through a musical analogy. The Fourier transform is like taking a chord and breaking it down into the individual notes that make it up. This is precisely how audio engineers analyze sound. This frequency spectrum shows how different instruments occupy different frequency ranges. When we apply the Fourier transform to a function like this one, we can identify patterns, filter out noise, and compress data efficiently. The Fourier transform has countless applications across various fields, including signal processing, image compression, audio analysis, and medical imaging. The core idea of the Fourier transform is that any signal can be broken down into a combination of simple sine and cosine waves. Let's start with a complex signal. This could represent sound, radio waves, or any other type of data. This complex signal can be decomposed into simpler sine waves. Each wave has a different frequency and amplitude. The Fourier transform tells us exactly which frequencies are present in our signal and how strong each component is. The Fourier transform converts our signal from the time domain to the frequency domain. Each spike represents a frequency component. Here's a practical example of signal decomposition: amplitude modulation used in radio broadcasting. In this process, a high-frequency carrier wave is modulated by a lower-frequency message signal. The Fourier transform helps us analyze the resulting wave and extract the original message. The Fourier transform gives us powerful insight by decomposing signals into their fundamental wave components, allowing us to understand, analyze, and process complex signals in ways that wouldn't otherwise be possible. For a continuous time signal, the Fourier transform provides a mathematical way to convert a signal from the time domain to the frequency domain. Let's break down what each part of this equation means. F omega represents the transformed signal in the frequency domain. The e to the negative I omega t is a complex exponential function that combines sine and cosine waves to analyze frequency components. Omega represents the angular frequency, which is 2 pi times the frequency in hertz. And the integral from negative infinity to positive infinity means we're looking at the entire time span of the signal. This equation essentially calculates how much of each frequency contributes to the original signal. You can think of it as finding which sine and cosine waves, when added together, recreate your original signal. Don't be intimidated by the equation. It's really just a way of mathematically expressing the decomposition of a signal into its frequency components. The Fourier transform converts a signal from the time domain on the left to the frequency domain on the right. This powerful transformation lets us analyze which frequencies are present in a signal. This mathematical foundation is what enables practical applications like audio processing, image compression, and noise filtering. Now that we understand the mathematical representation, we'll move on to explore how the Fourier transform differs from the Fourier series. Let's explore the important distinction between Fourier series and Fourier transform. While both analyze signals in terms of frequency components, they serve different purposes and apply to different types of signals. The Fourier series is designed for periodic functions, while the Fourier transform handles non-periodic functions. A periodic signal repeats at regular intervals. For example, this square wave repeats its pattern indefinitely. The Fourier series decomposes periodic signals like this square wave into a sum of sine and cosine waves. In contrast, a non-periodic signal does not repeat regularly. Many real-world signals like speech, music, or a damped oscillation fall into this category. For these non-periodic signals, we use the Fourier transform, which converts a time domain signal into its frequency domain representation using an integral. Both the Fourier series and Fourier transform allow us to view signals in the frequency domain rather than the time domain, revealing their component frequencies. The key difference is that Fourier series works with discrete frequencies for periodic signals, while Fourier transform handles continuous frequency spectra for non-periodic signals. Noise cancellation headphones are one of the most common applications of the Fourier transform in everyday life. These headphones use advanced signal processing to analyze ambient noise and create audio signals that effectively cancel out unwanted sounds. The basic principle behind noise cancellation is simple: detect unwanted noise and generate an anti-noise signal that cancels it out. The Fourier transform plays a crucial role in this process. It converts ambient sound from the time domain to the frequency domain. This allows the headphones to analyze the frequency components of the noise in real time, identifying what frequencies need to be canceled. Once the headphones analyze the ambient noise, they generate an anti-noise signal, essentially the same sound wave but inverted. When these two waves combine, they cancel each other out through destructive interference, resulting in silence. To capture ambient noise, these headphones use small microphones mounted on the outside of each ear cup. The audio signals are then processed through a sophisticated analysis system that extracts frequency features using the Fourier transform. This entire process happens in real time, allowing you to enjoy your music or podcasts without distracting background noise.
The Fourier transform has enabled remarkable advances in medical imaging and vibration analysis. In medical imaging, particularly MRI technology, the Fourier transform converts the radiofrequency signals emitted by hydrogen atoms into detailed anatomical images. The process involves collecting raw signal data, applying the Fourier transform to convert time domain signals to frequency domain information, and reconstructing detailed images of internal structures. Vibration analysis is another powerful application of the Fourier transform. It decomposes complex vibration signals into their constituent frequencies. This frequency domain representation helps engineers identify mechanical issues before they cause catastrophic failures, detect structural resonances, and perform quality control in manufacturing processes. The principle extends to multiple dimensions with the 2D Fourier transform, which is essential for processing two-dimensional signals in medical imaging. According to industry experts, representing vibration signals in the frequency domain allows engineers to relate them with key operational parameters of machinery, providing insights that would be impossible to detect in the time domain.
The fast Fourier transform, or FFT, is an efficient algorithm for computing the discrete Fourier transform. It allows us to convert digital signals from the time domain to the frequency domain with remarkably improved computational efficiency. The computational efficiency of FFT is dramatic when compared to the standard DFT algorithm. The standard discrete Fourier transform algorithm has a time complexity of O of n squared. The fast Fourier transform reduces this to O of n log n, which is a massive improvement for large datasets. This efficiency difference is particularly dramatic as the input size increases. Let's look at a real-world application of FFT in GPS signal analysis. In this example, we see a noisy GPS signal in the time domain at the top. The FFT transforms this into the frequency domain, shown in the power spectral density graph at the bottom, revealing the key frequency components. The fast Fourier transform has revolutionized numerous industries. In telecommunications, it enables efficient signal processing for everything from cell phones to satellite communications. Multimedia applications benefit from faster audio and image processing. In data science, FFT makes it practical to analyze large-scale data sets. Industries have reported efficiency improvements of up to 50% compared to legacy processing methods by using FFT. As mathematician Gilbert Strang noted, The fast Fourier transform is considered the most important numerical algorithm of our lifetime. As we look to the future, the Fourier transform will continue to evolve with advancements in algorithms and computational hardware. Future algorithms will significantly reduce computational costs, even for incredibly large-scale datasets. Its integration with machine learning frameworks is opening new possibilities, enabling deeper insights and improved model performance across various domains. Research into hybrid classical quantum computing approaches promises to unlock entirely new frontiers in data science, where quantum Fourier transforms could revolutionize computation. With these advancements, the applicability of Fourier analysis continues to expand across disciplines, from next-generation communications to advanced biomedical imaging. As we've seen throughout this exploration, the Fourier transform will remain a fundamental cornerstone technique in signal processing, communications, imaging, and emerging domains. From classical signal analysis to quantum computing and beyond, the Fourier transform continues its profound mathematical legacy as one of the most important tools in modern science and engineering.